Good morning. So this week I'm going to cover Chapter 8, which is on deadlocks. Now it's been a topic we mentioned a few times, but this entire chapter is devoted to deadlocks, different ways deadlocks could happen and ways to handle deadlocks. So first is a system model and the different characterizations of deadlock, ways of handling deadlocks, and four of them are first prevention if possible, that is, don't make it happen. But if you can't prevent, you could at least try avoiding. And then if you can entirely avoid, you need to try detection. So that is, as it's running, you periodically sample and check if it's stuck in a deadlock condition. And when deadlock actually happens, then what do? Well, you try to recover from it. So these are the four different levels of how one would handle deadlocks. Of course, you prefer to prevent whenever possible, but you can't always do that because to do prevention, you actually need to know certain things in advance, that how much resource that a particular process may be requesting. And it's a protocol, so they make a promise and they better stick to their promise. If not, then the system can only do its best trying to do what's promised. But when the actual usage exceeds what was promised, then all bets are off. So deadlock could still happen. So the best they could do is to try to get some processes unstuck, and so some will live on, others may die. Okay, so here's the problem. So you have a set of processes that are all blocked, but when they're before they get blocked, they hold some resources, and when they are blocked, the resources they're holding continue to be held and could not be released during that time. Okay, and why are they stuck, or why are they waiting? Well, they're waiting to acquire some resource. But this resource is held by some other process, right? So you have a cycle somewhere. So you have a circular dependency. So everybody's waiting for somebody else to release a resource so that they can get unstuck, but they can't get unstuck because they hold a resource that somebody else, they can never acquire that resource because somebody else that holds a resource they need is depending on the resource you're already holding, you're not releasing. Right? So you have that circular dependency. So here's one example: two processes, two tape drives. Each one is currently holding one tape drive, and each process is requesting another tape drive. Why would you want to do that? Well, maybe you want to do a tape-to-tape copy, right? So you want to read from one and then write to the other, but your buffer memory is probably not big enough, so you want to acquire both and read from one a little bit, and at the same time, well, you write to the other. Maybe you pipeline them. And maybe two processes want to do either the same or maybe in opposite. Maybe one wants to copy from tape drive 1 to tape drive 2, the other way around. And so they acquire in an order that happens to cause the circular dependency. Another example is you have two processes. They don't have to be physical resources. They could be just semaphores, right? Semaphore A and B. And so P1 holds resource, or actually holds B, waiting for A, right? So then it does a wait on A, then it will do the signal on B. So that means you're not just doing a wait on a single semaphore. You actually have multiple, but you do them in a sequence. Whereas P2, currently holding A, does a wait on semaphore B, right? And then after B does this thing, then it does a signal of A. So you can see if you do it in this order, then you could get into a circular dependency, which then is deadlock. Okay, and deadlock can happen with mutex locks too. So this is a typical example from the textbook. So you have a lock of mutex 1, lock of mutex 2 do the work, process 2, lock of mutex 2, lock of mutex 1, and do the work. What would be a real life example? Well, a transaction, for example, bank transaction. So what you want to do is, well, there may be two simultaneous transactions happening. One is you're on your ATM machine, you're withdrawing some cash. The other is your friend says, oh, I'm going to be nice, I'll give you some money. And then they're doing a transfer, right? So the reason you want to do two locks is because, well, you want to make sure that when I deduct money from one account, I actually put it in the other account and vice versa, right? So then that means either I deduct and add, deduct from one account, add to the other account, both or nothing. Otherwise, you have inconsistency, right? Somewhere money is missing or somebody gets extra money, who pays for it, right? So that's why they need to do locks on both accounts at the same time, because they want to make sure in that critical section you are doing a transaction, which is all or nothing, right? And so you could have simultaneous transactions, right? Because one could be one transfer, and who knows another transfer, your payroll, school's paying you salary, or your company's paying you salary. At the same time, you're transferring money to like utility company, whichever, right? So these things can be requested at the same time. So you want to make sure they are both locked. So you need to. That's why you need to acquire both locks. But who's to say which order you should acquire these locks, right? You might say, well, maybe I always acquire the lock from the account I'm withdrawing from, and then second mutex would be account I'm writing to. But then you could have, at the same time, drawing money from that account as well as somebody putting in money, right? So then it's very hard to then ensure that you lock these in the correct order. So like mutex 1, mutex 2, these could correspond to the mutex locks to these two accounts. And so, and if you do both processes, mutex 1, then mutex 2, then this wouldn't have that problem, right? You wouldn't have a deadlock problem. Because by the time mutex 1 locks, process 2 couldn't be in there. Or process 2 can even, or if process 2 is holding mutex 1, you could process 1 would have to wait anyway, so that would be okay. So this one, right? This if each one acquires one mutex and then gets swapped out, right, and it is blocking on the other, then you have a deadlock. So this is a particular order where deadlock could happen. Now there's a difference between a deadlock and a live lock. Okay, they are both bad conditions to be in. Deadlock is worse in the sense that all processes with a circular dependency are blocked, and you can't make progress because they're one's depending on another, they're depending on another in a circle. Whereas a live lock, these processes are not blocked. They're doing work. They're busy. They're trying, but not productively. What's an example? Well, so imagine, remember in Python you could have these non-blocking attempts to lock, right? You can say like blocking gets equals false as a parameter. So yes, you could actually do kind of a polling version. So you keep trying to acquire a locks or a mutex, but who's to say you will get it? Yes, it's non-zero probability you can get it, but you could just be in a bad. You could just keep having bad luck, and it's more than luck because why? Because of scheduling and also because of timing. Sometimes it's called phasing, right? Anybody who took any like physics, right? You have waves, right, and different frequencies, right, or even double E. If you schedule the code, or this code is scheduled so that the phasing doesn't change, or it doesn't change very much, then yes, you could actually get stuck always in a bad situation. And every time you come back, somebody has already acquired it in front of you, and you could always come in second and you never get it. Right? Next time around, somebody always comes before you, right? There's not a queue there or aging to track your attempts. So you could keep failing, right? And that would be an example of live lock. And another would be, those of you who have taken communication probably know Ethernet, right? Or even Wi-Fi. Wi-Fi is based a lot on Ethernet concept, except Ethernet is wired, Wi-Fi is wireless. So how does that work? So basically, anytime you try to transmit a packet on Ethernet, you just try, but the channel is shared with other nodes, other computers, other devices, and so you could collide with somebody else, right? So first you check, is the channel busy? Not, then you go ahead. But then somebody else could also go ahead, right? So so what you do is try to sense if there's collision. If so, then you back off and you retry. But what happens? Well, if everybody backs off and retry at the same time, after a certain delay, and same delay, guess what's going to happen? They're going to collide again. They keep colliding, and then nobody wins, right? So the way Ethernet solves this is when it detects collision, you pick a random number as your delay before you retry. And so chances are one will succeed, the other may succeed too if the one that goes first finishes, right? So the solution is the randomized back-off delay. And so there are several ways to address live lock, but that's more or less out of the scope of this class. So we'll focus on deadlock here. And to have a deadlock, there are 4 necessary conditions. Necessary means these 4 conditions all have to be true in order for the deadlock to happen. If you break one of them, then you don't have a deadlock, which is good news, because then you just have to pick one that you can break. Okay? Then you don't have a deadlock. So number 1 is mutual exclusion. That is a necessary condition for a deadlock. That means only one process at a time can use a resource. 2 is this pattern of what's called hold and wait. Okay, so that means if all you're doing is acquiring a single mutex, then that's okay. But if you acquire one, you hold it, and then you try to acquire another one before you release that other one, right? Like we've seen in the case of bank account locking 2 accounts before doing the transaction, then yes, that's the second necessary condition. So that means a process holding at least one resource wants to acquire another or more resources, but that's held by other processes, so it has to wait. Okay, so it already successfully acquired some. Now it's waiting on somebody else to release that resource it wants. Number 3 is no preemption, but it's not what you think. It's not the process scheduling a preemption. It's the resource sends a preemption. It's like, what does that mean? Okay, so with the process, what you're doing is and running, and then whether you make a system call, whether you context switch, a timer comes and you do a context switch. So the OS saves the state somewhere, and then restores the state, let other process run, and comes back to you, and then restore your state. So the process that got context switch didn't know. It's like, oh, okay, I just kept running as far as I can see. Time just blipped, and then next time, you keep running, right? Now, that was process scheduling type of preemption. Now, resource preemption, what does that mean? That means I do a wait. Hey, I got resource A, or I got semaphore A, whichever, right? That's really used to guard your resources. and while I'm holding it, preemption means OS steals that resource away from me while I'm frozen, and then somebody else gets to use that resource, and then before I know it, puts it back, and then I wake up. Oh, okay, book's still in front of me. Okay, that could happen. I mean, theoretically, a library could do that. So it's like that guy always carries down that book, never returns it. But there's some other guy that wants to read it really badly. So while they're sleeping, napping in class, and then they send somebody over, steal that book away from you, and then the guy checks, oh, okay, then puts it back before you wake up from class. Okay, so that's the form of resource preemption. Okay, you get that? Yeah. So so this is resource preemption. But if you don't allow resource preemption, which has been the case, right? When we talked about semaphore, we talked about mutex. Once you get it, you lock it. Right? We don't assume somebody preempts a resource, right? But and if you make that assumption, then yes, that's the third necessary condition for deadlock. But if you can allow resource preemption, so that means while you're napping and somebody steals the book from your bag and lend it to somebody else, and then before you wake up, put it back to your book, you never knew that somebody else took that resource while you were napping, then yes, that's then that you won't have a deadlock, okay? Because that actually directly affects number two. While you're holding and waiting, holding some resources, waiting for somebody else, that's when if the preemption comes and grabs some of the resource you're holding temporarily and then put it back, then yes, you're okay. There, I mean, it's like you haven't lost anything. Well, at least, but that doesn't always work. Okay, that it's only a property. Okay, so if your resource allows preemption, then that's okay. Then that's good news. But not all resources allow preemption. Okay, so that's number 3. 4 is circular wait. Obviously, you have to have a circular dependency. I'm holding something, waiting on somebody else, that then somebody else is holding that resource, but they're waiting on some other resource, and then it comes back in the chain. Okay, that's a circular wait. And that is the 4th necessary condition. So if you can break just one of them, you don't have deadlock. Okay? But doing resource preemption is very tricky. It's not just that sometimes you can't even do it for certain resources. Other times it's you just not it's just very costly, and so what would be an example? Well, one example is like supermarket checkout line, right? I have big cart. Maybe that's you can think of it as process scheduling, but I'm basically getting the the clerk as my resource. And so the clerk is helping me do the checkout. And so to preempt that is very hard, right? Because what do you have to do? They're in the middle of printing out a receipt. Do I pay first? Or do they just reverse, right? Do they just say, okay, no, I'm just going to clear out your receipt, put everything back into my cart, let the other guy go, then the other guy finishes, then should restart me? Right, that would be very expensive, right? Because maybe like 100 items, and I'm already into my 70, 80 items. Then you want to preempt my resource, and then because preempting a resource sometimes involves restarting, and that's drastic. Okay, so that's why you can't always afford to do it, because just that the cost for preventing deadlock by allowing resource preemption may be too costly. It may take such a big impact on your system performance that it's probably not worth doing. Okay, so that's why certain systems, they say, screw it, I'm just gonna let deadlock happen. If it happens, I'll catch it and try to break it, and that way I don't pay that heavy cost for trying to avoid or prevent deadlock, because that's way too costly. Okay, anyway, so system model looks like this. You have a set of resources, numbered from 1 to m. And these resources could be CPU cycles, memory space, I/O devices, like printer, tape drive, whichever, right? And each type of resource, okay, so R is resource type. Each type may have multiple instances. So for example, you may have multiple tape drives, multiple hard drives, even multiple cores, right? That's not too difficult to understand. And then sequence of steps in utilizing a resource. So what do? Well, pretty clear, request, use, release, right? A lot like our await, and then critical section, and then signal, right? So from this kind of system model, you can construct what's called a resource allocation graph, sometimes called system resource allocation graph. And so you can divide the vertices into two sets, one set for resource types, one set for the processes. And of course, what you want to do is to have the processes make requests to the resources, and then they may be treated uniformly so that as long as you say you want a resource of a particular type, I don't care which instance, the different instances may be treated all the same, but sometimes that's not the case. Okay, so you have a request and assignment. So assignment means yes, your request is granted. Now this resource is yours. So that's when you say whether you do a mutex lock or you do a semaphore, right? When you get past that, you're not blocked on that semaphore, not blocked on that, then you have that, right? And before you do a signal, that's when you still get assigned that resource. And the way you draw this on a graph is you have a directed graph. If it's one from a processor edge from a processor to a resource type, then that's a request. And if it's an edge from a resource to a processor, that's an assignment. Okay. And so you can do this. I mean, the book convention is processors are in circles, resources are in squares, and then if it has multiple instances, you have little squares inside a big square. Okay, and then you have the request instance, so that goes from process to resource, and if it's holding, that means yes, that's an assignment edge, goes from resource to process. So here's an example of resource allocation graph. 3 processes, P1, P2, P3. For resources, okay, by the way, this edition of the book, instead of process, they call it threads. But they're really using threads and processes interchangeably. So, yeah, just so that you know. Anyway, so processes 1, 2, 3, and process 1 requests resource 1. But can it get it? No, at this time, there's one instance and it's already assigned to P2. So P2 is holding resource 1 or an instance of resource 1. Now P2, while holding R1, is making a request to use R3. But can it get R3? Not yet, because it's currently assigned to P3. Now is P3 requesting anything at this point? Not really. So eventually P3 will give it back, right? That's the assumption. And then when it gives back, then P2 can be satisfied, right? Then can make progress. And then because now you have 3 resources, right? Because R1, R2 are already assigned to P2. And R3 being requested, now if it gets granted, the arrow reverses direction, right? So if it has all the resources needs, it can make progress and then releases them, right? And once it releases, then P1 request can then be fulfilled because P2 just released it, right? And then now P2 has both R1 and R2 that it requests, then P1 can make progress. So in this case, it's conceivable that there's not a deadlock. However, if you just add one edge, suppose P3 makes a request to R2, okay? that edge with the red label there, the diagonal request, what happens? Then a deadlock may exist. Does it just say it exists? Well, not necessarily, depending on your timing, right? So a deadlock may exist. Why? Because it just depends on where it's being blocked. So P1 waiting for P2 to release R1, and then P2 waiting for P3 to release R3, right? And then P3 waiting for P1 or P2 to release an instance of R2. And so there is a cycle there, or actually two cycles, right? Because it could be R1, or it could be through P1 or through P2. Okay, so now just having a cycle doesn't imply it has a deadlock. So here's an example where there is a cycle but no deadlock. So here P1 is requesting R1, and then but R1 is assigned to R3, and another instance is assigned to P2. P3 is requesting R2, but R2 is currently, there's two instances, one assigned to P1, one assigned to P4. And so why wouldn't this have a deadlock? Well, that's correct, because our assumption is that all instances are equivalent. So as soon as it gets an instance, it doesn't say which instance, right? If it really wants the instance held by P3, then you have a problem, right? You may have a problem, but but here you're assuming these different resource instances are equivalent. So as soon as either P2 or P4 is done, gives that resource instance back, then it's as good as any other instance. Then the request can be satisfied. Reverses direction, it's okay. All right, so big assumption. This is predicated on the assumption that all resource instances of a given type are considered equivalent. So you're not picky. Unlike you go to a haircut. Sometimes I just want that stylist, and because that stylist always does a really good job with my haircut, right? But then you might go in and there's 5 stylists there. They're just they don't have any customers, but you still choose to have your favorite stylist to get your haircut, right? And so then you're being picky there. And in that case, if you're so picky on that particular instance, then yes, you can still have a deadlock, right? But if you say, okay, no, any stylist can cut my hair in that shop there, then it's okay, right? Because you think all of them are equally good, but sometimes that's not the case. You just have your favorite haircut stylist. Okay, so basic facts. If such a graph contains no cycle, it means no deadlock. You can be sure of that. But if it contains a cycle, does that mean you have a deadlock? Well, it could be you have a deadlock, but it doesn't automatically imply you have a deadlock. It does imply you have a deadlock if there's only one instance per resource type. Okay, that's that mutual exclusion condition you saw earlier, one of the 4 necessary conditions. But if there's several instances per resource type, and you consider all instances to be equivalent, then there's just that possibility of deadlock, but it doesn't automatically imply deadlock. Okay, so that's the distinction. And so there are algorithms for prevention, avoidance, detection, and they all need to know: do you have multiple instances of a particular type of resource, or do you have just a single instance? And the algorithms, as you can imagine, would be much simpler if you just have one instance per resource type. If you have multiple, then it gets a little bit more involved, but still doable. Okay? So 4 ways to handle deadlocks. If you can prevent, great, because prevention means you ensure that these necessary conditions cannot hold. In fact, if you ensure just one of the necessary conditions cannot hold, then you're good, right? But that's sometimes harder than it seems, okay? Because these necessary conditions all have to be ANDed together. If you break one of them, no deadlock, but they could be harder to break than you might think. So if prevention is not possible, then you try avoidance. Avoidance means what? Means at runtime, you check first. And you check, hey, can I possibly get into a deadlock? Then if so, I avoid it. Okay? But does that guarantee you won't get into a deadlock? Depends, right? But it's not as strong as prevention. Avoidance just does the extra work at runtime, hoping you don't get into a deadlock. Or at least if you think, oh, there's a possibility of getting a deadlock, let's avoid that. Okay, let's not get into that situation. That's risk prevention, but then that may be too strict. Now, the third option is deadlock detection. So it says, well, if you do whatever you want, and if deadlock happens, I detect it. Oh, okay. Then I try to figure out what to do with it. Okay, and that is what most systems do. Isn't that kind of scary? Your OS could actually get into a deadlock. It doesn't try to say, hey, you could get into deadlock. Just says, let it happen, and then so it will periodically come and sample, or by sampling, it actually goes through and checks the resource dependencies to see if there's additional pending requests compared to these other ones. And then, so it's a little costly. That's why it couldn't do it every single wait and signal. It has to do it once in a while and then checks it, right? And figures out what to do. Now, what can it do? Well, several things. One is it could try to recover, and what can it? But then recovery usually is less than satisfactory, because I mean, in best case, you could restart some process. I mean, you preempt them and then grab the resource back. So it's not like library really needs a book back from you. You're still there, and then you still want to read several books together, and you already checked out a big stack, and then they would knock you out, and then you got unconscious, and then they grab the book back, give it to all the other ones who need it, and then before you wake up from being knocked out, then they put these books back into your bag. Well, that could be one way. So that's restarting. Or maybe worst case is you wake up, hey, where are my books? Okay, so somebody grabbed them, right? So then wait, one more time, you go to the library and then check out these books, right? So that would be to restart the process, right? So recovery can be kind of drastic, okay? So that's why, but then the hope is that this doesn't happen so often that you shouldn't have to do it. And then once in a while, if it gets stuck, I mean, Windows users used to know this. Yeah, okay, reboot, right? And then that solves the problem. Nowadays, Windows got better, but still. Anyway, so yeah, believe it or not, most systems just prevent deadlocks. Well, really not going to happen. If they happen, users will figure out what to do. They just reboot. That's the sad reality. But anyway, deadlock prevention, that's the strictest form. So that means there's a lot of limitations, a lot of restrictions on the ways that requests can be made. And this is raised to a higher level. So what does it take? Well, it takes breaking just one or more of these necessary conditions for deadlock. Remember, mutual exclusion, hold and wait, no preemption of resources, not of processes. Not process, of course, no, that's given, because you wouldn't have a problem if the process weren't preemptive in the first place. So no preemption of the resource, and circular wait. If you can just break one of them, yes, you've succeeded at deadlock prevention. But that's not always as easy to do. Okay, first, deadlock prevention. So that means you simply disallow mutual exclusion. It's like, what? Really? That's kind of strict. So, I mean, you can share resources without locking. So, for example, if you do read-only, I'm just reading a file. Yeah, you don't need mutex on that. And you could use counting semaphore with a really high count, assuming you have enough instances. Then it won't exclude you, right? So that you're hoping it wouldn't, but that wouldn't be to prevent. That's really just to minimize the chance. But some resources do require mutex. We saw examples: tape drive, printer. Well, even though printers usually have like a spool, so that means your request is decoupled from the actual acquisition. But still, somewhere, this is not so much user level. This is at least some system level level. They still have to mutually exclude each other. And once you start accessing a tape drive or something, then you really have to use it for the duration. It's hard to, or not very efficient to kind of multiplex between different processes, because like the tape drive, it takes a long time for the reel to spin to the beginning, and maybe several minutes later to spin to the other end, right? That's just very inefficient. And so now I'm a little picky about the terminology used by the book. The book calls these non-shareable resources, but no, I think that's a bad term for it. They are not simultaneously accessible. They are certainly shared. They're just not shared at the same time. Okay, so so that means over different times, yes, they could share, but they're not shared at the same time. So yes, the point comes back to some resources require mutual exclusion, therefore you can't apply this deny mutual exclusion as a way to prevent deadlock. Okay, so really limited by the nature of the resource. But if it's CPU time, easy. If it's CPU register, easy. Share memory, easy. Okay. Now, can you eliminate hold and wait? So what that means is you want to make resource allocation more atomic or more like a transaction. So all or nothing. Here, I need to request one instance of resource A, 2 instances of resource B. And so you force the user to say, okay, now if you want to request these, make these requests simultaneously. And that's all you are allowed to do. You can't say request A, and then next call request B, and then next call request another one, right? So you say submit all your requests simultaneously, and that's all you get to do. Once you submit, you can't. Well, so does that help? That kind of helps, right? Because then, in the sense that, then that way, there's not that circular dependency, because I get all the resources, and then once I don't block on waiting on any other resources, right? Then I finish, and then I release all of them together, right? So because once I acquire all my set, I don't block anymore, so I can't get into a deadlock, right? Or I'm not part of a deadlock. And if everybody works like this, then nobody gets into a circular dependency. So you could, well, but there's two different options. One is before a process starts, it has to say, I want to request these resources even before it starts, and the system makes sure that yes, before I launch the process, spawn the process, it already gets the resource for you. But that's a little too restrictive, right? Because resource use inherently is a dynamic type of thing, right? So you want to use, especially for something you just use temporarily, a little while, and then you give it back, right? And that's how you can achieve good utilization. So option 1, way too restrictive, too static. Option 2 requires that you can only make one batch request at a time. And once you make it, you make another batch request. So that's another way of paraphrasing number 2, option 2, which is process must hold no resource before making that batch request. So, right? So that's that is one restriction you could make, and so that means before you get additional ones, well, you have to release all the ones you held, or you batch them, batch the request. So a lot like library. That means the library allows you to check out, like if you want to check out 5 books, you can't say I go one book and then while I still hold one book, go and check out another book and then do it over different times. The library may require you, okay, you make all your requests in one shot. If you want 5 books, let me know the 5 books, and then you check out the 5 books. Then while you're holding any book, you're not allowed to check out any more books. Okay, so that's kind of what it's saying. That does prevent the hold and wait, but and then when you return books, you have to return all of them. You can't return just the ones you finish. Then the disadvantages are, well, it's lower resource utilization. In the sense, it's analogous to the concept of fragmentation. But it's fragmentation over time. We'll talk about fragmentation when we talk about memory. And even if you don't have deadlock, you could still have starvation if you do it this way. Okay, so still, this is good idea, but a little too restrictive and could impact system performance a lot. Number 3, how about allow resource preemption? So I talked a little bit about this. So temporarily take away resource already allocated process, PR. So that means you checked out a book, but library says, hey, somebody really needs it, or else they get deadlocked. And then so you're forced to temporarily get back, or they steal the book back from you, lend it to somebody else, and then before you know it, they put it back to your bag. Okay, that's resource preemption. And in fact, they wouldn't just release one, they would release all the resources acquired by the process, and so that other processes get a chance to use these resources. I mean, okay, so that's really like the worst case. They would release all the resources acquired so far. So that's a lot like context switching, but for a different purpose, right? I mean, in that it's context switch. So just as context switch allows you to protect CPU as a resource, this kind of resource preemption allows you to utilize other processes to utilize the resources as a way to protect the system, right? And OS does need to track and reacquire resources that so that makes your semaphore much more complicated, as you can imagine, right? It's not just you put somebody on wait queue. You have to track additional state. Hey, am I going to steal this resource back, right? So this guy's on wait state on a different semaphore, but then I need to know what other semaphores they've already successfully entered, and then temporarily change those, and you have to do a lot of bookkeeping. And that's assuming you could even do that in the first place, okay? And depending on the resource, so if it's just CPU resource, like a shared memory or some other state thing, then it's okay. But if it's an I/O device, then that would be kind of bad, because say, I mean, with a tape drive, you probably don't want to do a preemption like that. I'm in the middle of writing or copying or backing up to a tape. And then what does it mean to preempt? I mean, it has a lot of other bookkeeping required, right? Because it does have to keep track of a lot of like the directories, file size, the file pointer, all that. Then if you preempt it, then what does it really mean? Then, or even in the case of transaction, I'm doing a bank transfer. In the middle of bank transfer, is it even a good idea to do this, right? And so a lot of times you actually have to restart in order to have that transaction semantics to be consistent. But then restarting could be very costly because who knows, it's not just reading some memory location or reading a file. It could involve many, many steps. There's encryption involved, there's transmission, syncing up with lots of different things, logging. So, so this is quite different from just context switch. Context switch, you save and restore state. With resource preemption, you may actually have to restart. Okay, so then and you have to restart so that the process itself can actually execute smoothly. And do you even expose this to a language level? Hard to say. Right? But then it would probably have to do more, right? If it preempts and then you're waiting on some other resources, then when do you put this process back on ready queue? So you probably do it at the time when these other resources can all be acquired, then you give them all in one shot and put this process back into its ready queue, right? So this really complicates a lot of the mechanisms. And it's not always applicable to all resources. So applicability, resources with state can be easily saved and restored. Yes, that's fine. CPU register, memory, database transaction, even though that may involve some restart, but not applicable to mutex log, semaphore, printer, tape drives. Right? So yeah, so if you want to do this in semaphore, it's very hard. And if you don't even know the semantics of the resource that the semaphore is guarding, you can't really do this in general. I mean, you could still do it for specific cases where you know the semantics. And it may involve some restart semantics. And you may have to bring this up to a language level. But in general, so that's what the book says, not generally applicable. So generally, that's a qualifier. So that means if you don't know what you're doing, you can just implement a general semaphore with resource preemption or mutex with resource preemption. Because that's dangerous. You don't know if that. I mean, semaphore is just really a way to allow multiple instances or a way to implement mutex, right? It doesn't really know the semantics of that resource. Okay, so how can you break circular wait? And well, that is one way you can possibly do it. So you saw the transaction part where you lock one and then lock another one before but then you lock them in reverse order. That's where you can get into deadlock. But if you lock them all in the same order or have some total ordering, so say tape drive always order 1, disk drive order 5, printer order 12. And if you acquire these multiple resources, you are required to always go from low number to high number. If you do that, then you can actually prevent deadlock. Why? Because you always get locked out by the outermost, right? And then when you release, you have to do them in reverse order, right? So if everybody gets locked out by the highest, then there's no way they could have that a dependency back to a lower one, right? Because that's by construction. So the counterexample doesn't exist. So process, request R0, process, and R1, and so forth. And then there's really, you can't go back to, once you can have a chain, but that chain never closes the loop because it never goes back to a lower number resource. Okay? If everybody does their request this way. All right, so this may be a way to do it, but then it requires everybody to follow this protocol and the code to be written in some kind of total ordering that may be a little hard to enforce in general. Okay, but the system may try to enforce this at runtime and say, hey, you just requested a resource with a lower number than the one you're holding, and reject that. So runtime, you could try to enforce this. So it looks like 4 may be the most feasible of the 4 conditions for deadlock prevention. Okay. And here's just some examples. I mean, you've seen this. It's just in pthread mutex lock, and that was the first and mutex and second mutex. But even if you write the code like this, it could still be the case where somewhere at runtime, additional work is done so that the total ordering can be enforced by another API. So you just say, well, I'm requesting one and the next, and so then that way, it does involve a little bit clever programming to make sure you request these resources in total ordering, because you can't just tell from the first mutex, second mutex. They could correspond to things, because these are variables, right? They could correspond to something with higher or lower total ordering. Okay, so then, yeah, so then this is the kind of clever programming needed. So you have like transaction example from and to. So you then have to call a separate API to get a lock for the from and get a separate API lock to. And then they need to have some kind of total ordering or enforce the total ordering such that you can't, your system may disallow you from violating that total ordering of requests. Okay? And this way, you won't get into a deadlock. But then if you don't, if you just do from and to without considering total ordering by that API, then yeah, you can imagine everybody does the from and to, and one from could be another to, right? The actual account may be different.